Hello everyone. Today's topic is IBM Watson Studio Local, and specifically we are going to talk about the considerations for running big workloads on IBM Watson Studio Local. Now, typically, when you're using a platform like Watson Studio, you would have an environment or a sandbox environment, so as to say, and this sandbox environment is provided as an experimentation environment. And depending upon the infrastructure that you have, it may have any number of nodes, starting from 3 nodes to could scale up to any number, literally. This area is usually connected to the production network so that we can extract data and connect to production data sources. But this is considered a sandbox environment and not a production deploy environment. In addition to this environment, you would have a deployment environment where after the experimentation is done, after the model training is done, it may be deployed for regular retraining or for regular inferencing, and usually that happens on much bigger a workload of data. The data sources could be a variety of sources. It could be traditional data warehouses such as DB2 warehouses, or it could be big data environment like Hadoop ecosystems with files and HDFS and Parquet and different formats. Now, for the considerations of running the workloads, the most important aspect that we have to take note of is the amount of resources that's available in each of these regions. Typically, the experimentation environment may be a big environment having lots of CPUs and RAMs, or it could be a relatively smaller environment with having maybe just 3 nodes or 4 nodes with limited amount of CPU and RAM. Similarly, the deployment environment, depending upon the workload, may have been designed with a much bigger capacity with lots of CPUs and GPUs and memory, or maybe it has been done for a POC purpose, in which case the deployment environment may be much smaller, maybe because we don't have a lot of production grade workloads to be deployed. But either of these environments can be scaled horizontally by adding more nodes to the cluster. And Watson Studio is from a licensing standpoint is licensed by number of users and not by compute, and hence there is no licensing impact if we decide to scale it up by adding number of nodes. The other aspect to note is how much of capacity and how much of system resources we have on the source system. So typically, if we have a data warehouse, the data warehouse, depending upon its implementation, can be a large distributed data warehouse with an MPP kind of architecture with in-memory tables and columnar databases, just the way you would configure for an analytical data store. Or it could be a very small data warehouse or very small database which contains less number of resources, like maybe it has only 4 cores or some 8 GB or 16 GB of RAM, in which case it's really a small database. And the same applies to Hadoop. The Hadoop cluster internally will also have its runtime and will have its data nodes, and based on the configuration, it may be a big cluster which can be leveraged to run big workloads, or it could be a small cluster. Now, for Watson Studio, typically, the recommendation is that any kind of experimentation that the data scientists are doing in a collaborative fashion, they should leverage the Watson Studio environment for that. And the reason why that is recommended is because Watson Studio gives us a number of runtimes and a number of IDEs and different versions of those runtimes and kernels that gives certain amount of flexibility to the data scientists to choose the right IDE based on the skill set and preference. Now, once this experimentation is done, maybe with a sample set of data, and we need to execute this on a much bigger scale, then we would need to deploy this workload on a cluster which has the right and adequate capacity. And typically that could be the deployment environment, or it could be the data sources themselves. Maybe we can leverage the cluster, the Spark cluster we have on Hadoop, and deploy it there if the especially if the data sources are there. Or maybe we can push down the data prep components to the data warehouse and do a lot of the data preparations inside the data warehouse, and then extract an aggregated or a much smaller set of data to do machine learning inside Watson Studio. So there are few different options, and along with these few different options, there are considerations that we need to have, and based on those options and considerations, and based on the network capacity and the cluster and compute and memory capacity that we have in the different regions, we can decide the best way in which we can optimize our workloads. From a Watson Studio standpoint, it does support the ability to run workloads locally, in which case we extract all the data from the source systems into the Watson Studio environment, and then leverage the runtimes available in Watson Studio to execute it. On the other hand, it also does allow us to push down the workload into an external Spark cluster, and that Spark cluster could be the Spark cluster of the Hadoop itself, or the Spark, or any other external Spark cluster for that matter. Now, the difference between using the Watson Studio environment and the laptop environment should be taken into consideration because the behavior of the users needs to adapt when they move from a dedicated environment with a certain amount of fixed capacity which are meant only for their use, to a shared environment where a lot of data scientists are kind of sharing the capacity of the cluster. So the key differences between these two environments is, one is meant for collaboration, where a lot of people are coming together and working together, and there's, from that sense, there's this sense of multi-tenancy and sharing resources, whereas the laptop is a single user system with a dedicated amount of resources. Watson Studio can be multi-node, so you can actually have a cluster of nodes which can scale horizontally, which means that if you need to run a workload, you may be able to leverage the capacity across all those nodes and get a much bigger compute than you can get in a laptop environment. Similarly, in Watson Studio, you can configure the capacity, whereas in laptop, it's kind of a fixed capacity, and you cannot scale it beyond that fixed capacity that you already have. Now, why those considerations were important is because when you go about executing bigger workloads, you have to pay some, you have to take cognizance of all these factors along with the capacity that you have for the different environments, and then decide on what's the best approach to execute these workloads. Now, let us now go back to our original topic, which is basically our requirement of being able to run bigger workloads using Watson Studio. And there are a few scenarios that's possible, a few combinations or permutations of how we want to execute that's possible, and we are going to explore all of them. The first one that we are going to explore is the scenario where we have the input data or the training data as a file externally, and it has a significant amount of data, maybe hundreds of millions of records. And then the way we want to execute is we want to load all that data into Watson Studio and then execute it in Watson Studio using the local compute in Watson Studio. So, and then once that initial training is done, we can deploy this to run on as a bad job in an external Spark, or maybe in a Watson machine learning environment, which also has Spark. The second scenario that we're going to consider is similar to the first scenario, that we still have tens of millions of records, or hundreds of millions of records that we need to use for training purposes of a model. But the data, instead of being in a file, is in some database. Now, in this particular scenario, instead of copying all that data into the local storage, we are going to read that data directly from the database onto the Spark memory in Watson Watson Studio and do the pre-processing of that entire volume of data within the Watson Studio Spark. And after the pre-processing is done, we are gonna use that cleansed data to build the model and then score the model and maybe store the results in a local storage. Once we are happy with these model building exercises and training exercises, we may deploy the model into a Watson machine learning environment and use it for scoring. The third scenario that we are going to look at is similar to the second scenario in the sense that here also we have the data in a database, but instead of reading all that data directly into the Watson Studio Spark, in this particular case we are going to do the pre-processing of that data within the database itself by executing the pre-processing queries in the database, and those queries can be submitted from the Watson Studio environment. And on completion of the pre-processing steps, the result data which is cleansed and which has been aggregated probably is then extracted from the database to the Watson Studio Spark, where the actual model training and the fitment can be done, and then on completion of that exercise, the results stored in the local storage. And then, like in the previous cases, once we are happy with the accuracy of the model that we are getting as part of this training exercise, we can deploy the model in a Watson machine learning environment for batch scoring or for training with bigger sets of data. So the difference between this scenario and the previous scenario is that here part of the pre-processing, or maybe the whole of the pre-processing, is pushed down to the database. Now, whether this will give us better performance than the previous scenario where all the data was extracted and loaded onto the Watson Studio Spark really depends on the amount of capacity and the amount of resources we have in the two compute environments. So that's the database and the Watson Studio. Now, in the environment that we are using, the database is pretty small. It's a 4-core database, and the Watson Studio environment is a 48 cores capacity with spread across 3 different nodes of 16 cores each. So in this particular case, it might be that the second scenario works better than the third scenario, because when we push down some workload into a database which is relatively small, then it might take it might take more time than it would if I run it in a bigger cluster with 48 cores. But this is really implementation specific. In your environment, if you have a much bigger database, then likely that you would be able to get better output from the third scenario. Also, in the third scenario, what we would see is once we do the pre-processing and some level of aggregation and feature derivation within the database and then get the data extracted out, that volume of data is much smaller than the original data that we had extracted, which would mean that I would need a much smaller Spark cluster in the Watson Studio environment. So in cases where your Watson Studio environment is not very big, it's reasonably small with 3 nodes, and you have finite constraints in the amount of memory that you have available there, one way to circumvent that problem is by pushing down some of the pre-processing steps to the database and getting an aggregated data out, which will require a much smaller Spark memory on the Watson Studio cluster. So these are the three scenarios that we are going to look at in Watson Studio. But before we do that, let us look at the typical steps that we would need to go through in order to make it happen. So first and foremost, we have to definitely get the data loaded, and upfront we would have the data loaded to Watson Studio. We'll have the data loaded to DB2, and as part of the scripting, we can read the data from DB2 itself. The second aspect and the area of consideration would be how we can go about setting up our Spark environment, how we can modify these Spark environments, what are the different options we have, and how do we select the right size using the Watson Studio capabilities. So once we have the right Spark environment, we are gonna run some training and testing scripts, and then once we are happy with the test results, we can save the resultant model and perform some online and batch scoring. Another aspect that we have to keep in mind is that because Watson Studio is a shared environment, we have to make sure that if we are not using an environment and we have a runtime which is kind of active but it's not doing anything and it's taking away some memory from the system, then it's always a good practice to go back and check on those active runtimes and stop those active runtimes so that the resources they are occupying can be released back to the system pool, which can be used by someone else in the team. So that's one discipline that we need to have in these kind of scenarios where we are trying to share a clustered environment among a group of data scientists. Finally, like the way we had configured the Spark environment for model training, we may want to configure the Spark environment for a batch scoring. And then once we have identified the right Spark environment, we can see how we can execute a scoring job and deploy it in batch over a big volume of data, and how we can go about executing, getting the batch results. And as we do this over and over, we can have multiple versions of the models created, and then we can also see how we can compare the accuracy of these different versions and decide which one will be the champion and then which one will be the challenger models. And over time, based on the comparison of these accuracies, we can promote one of the challenger as champion and vice versa. So with that, let us move to Watson Studio and see all these in practice. We are going to use this project, Customer Churn Lab, to demonstrate our scenarios. Now, in this project, I have added a couple of data sets. One is a CSV file, which is this customer churn 1 million records file. And also in parallel, I've also added this data source, which is essentially a DB2 table. And in this DB2 table, which is on cloud, I have also added this customer churn 1 million records. It's essentially the same data. This one is in a DB2 table and the other one is in a flat file. To load this 1 million records into the Watson Studio, it takes around a couple of minutes. If you're loading bigger data sets like 10 million, 100 million records, it might take a while. But this is the upfront for the first scenario that we are trying to show, where we are loading the data manually into Watson Studio. We have to do this upfront, and it may take a couple of minutes for that to get loaded. To add the table, basically you can go to the data source and you can add a data source and you can specify a data source name, specify the type of data source that you want to add and give the JDBC connection and credentials, test the connection, you can create the data source. And once the data source is created, you can add the data set of that particular data source by selecting the schema and the particular table that you want to add. So now that we have both the data sets defined, let's go about setting up the first task that we need to do, which is specifying the environment or identifying the right environment that we want to use for the training job. So in the Watson Studio, we have this concept around environments, which is nothing but a set of environment definitions that's available for us to use. Now, these are actually runtimes with a certain predefined capacity and with some supporting kernels of specific languages and their versions. For example, you have a Jupyter with Python 2.7, Scala 2.11, Art 3.4, and Spark 2.0. Similarly, you also have a Jupyter with Python 3.7, and this one, if you want to use Spark with this, it comes with Spark 2.4. Now, we can start and stop these environments. So when we stop these environments, these are just images, and when you start any of these environments, then they become live instances on which our workload can be deployed. Now, apart from the start and stop, you can also specify some capacity against these environments. So, for example, this one, There's no fixed capacity assigned. So here, for example, if I want to use this environment and I know that I have to load a data which is 5 GB or 10 GB or whatever, then I can always reserve some memory and assign sufficient resources to the cluster to ensure that I have enough capacity or enough memory or enough cores that's required to process the job within the expected period of time. So we can set some of these capacity requirements here, save these settings, and restart the environment. And when it restarts, it will restart based on the capacity that we have defined here, provided that is available in the cluster. So for my scenario here, I'm not going to reserve this and cancel this out. So this one we have cancelled it out. We haven't reserved anything, but if you see this environment, say for example, I have actually reserved some amount of memory and some amount of CPU, and this is the environment that I want to use. Okay, so once I have configured the environment that I want to use, we can go back and we can start building the script or building the training artifact for the model in question. So to do that, there are a few different options. I can either choose to do it using a notebook, and I can do a Python notebook or an R notebook, or if we prefer to do so, we can use R Studio to do it. Or if we are not familiar with coding, or if we don't want to do coding, but instead if we want to use a canvas-based drag and drop way of building the model, we can use modular flows. So for our purposes, we are using a notebook to build this, and here I already have a sample notebook. So once the kernel is ready, so for example, you can see here the kernel, it says kernel busy, and then now it is connected. So once it is ready, the kernel will show us kernel is ready and is idle right now. So right now I have the runtime assigned, and I have opened up the notebook, and this is where I can build the script. I can write the script to build the model, and this is entirely based on coding. Now we saw one mechanism by which we can set the environment parameters or the environment capacity, the Spark cluster capacity specifications. But if we want to configure it from within the code, we can do that as well by using this piece of code. So here what we have done is we have created a Spark session instance, and for that instance we are listing the current configuration that we have out of the box. So if you see this, the executor memory is 4 GB, and this is the master, where the master is accessible, and there may be some interesting things which we might be interested in. So cores, for example, the maximum is allowed is 2 cores. Application name is notebook. The host is given out here, and the initial number of executors is assigned as 1. So dynamic allocation is enabled, and initial executors is just 1. So this is a really small Spark cluster. It looks like a 2 core cluster with just 1 executor node. So I may want to change this. So if I want to change this, then what you can do is you can just stop the Spark context here, and then based on how we want to allocate the resources, we can specify the maximum cores that we want on the Spark cluster, the initial number of executors. Instead of just 1 executor, we can specify this as 6 executors or 3 executors or whatever X number of executors, and then the core, I can assign X number of cores to each of those executors, and some amount of memory to each of those executors. So net what it would translate to is that although my node may be small, but I can have a large number of nodes, and I can have a lot of these executors assigned in each of those nodes with a certain amount of core, and this total I can get here, say for example, I can get 6 cores in this Spark cluster, and 6 multiplied by 3, I can get around 18 GB of memory in this Spark cluster. So this is how we can also specify in the configuration of the Spark, and once we create the new Spark context, we would see that the corresponding changes would have taken effect. So these are the new changes. I can check. This is so initial executors is 6, and then the memory is 3 GB for each of the executors. This is giving us a total of 18 GB and all. So this is one way, and I mean the one more way by which we can configure the Spark environment, and based on the workload that I have, then I can design my my Spark environment and assign it. And as long as I have enough capacity in my cluster to accommodate the specification that we are suggesting here, it will be able to get those resources and assign to the Spark cluster as required. Okay, so that's around setting up of the Spark environment. Now, once that has been done, then what we want to do is, in the first scenario, what we saw was we wanted to load the entire data set of 1 million or 10 million or 100 million, whatever the case may be, into this Spark cluster that we have defined. So that's what we are doing here. We are taking this whole file. This is the whole file. We are taking this whole file and we are loading it into a Spark data frame here. And once we have loaded it into the Spark data frame, I am looking at top 5 records of it, just to get an idea of how it looks like. And we are capturing the timings here so as just to see how much time it takes for us to load it. So here, for example, you can see the start time is 141, end time is also 141. So it didn't take much time, around 7 seconds it seems. This is 3 and this is 10, so it took around 7 seconds to load the data and into the Spark data frame and show the first 5 records. So it's kind of fast, and the reason why it is fast is because before we are doing this step, we have already loaded this file into the local storage of Watson Studio. So the file is available locally, and it can quickly load it into memory and show it to us in a matter of like few seconds. Now, the other scenario that we wanted to check was, what if instead of doing this, I have the data in a DB2 table, and as part of my scenario, I want to read the data directly from DB2 table into the local Spark data frame. So that's what we are kind of doing here. And here, if you see that we have defined this is my dataset info, and essentially what we are doing is a Spark session.read from a JDBC source, and in the JDBC source, the DB table I have specified as our table, the one that we are using, and then we are specifying the credentials here with which we can read the table, and we are doing a dot load. So once that is done, we are assigning that to a Spark data frame, and then we are showing the first 5 records just like the previous scenario. So here also the result is the same. Now if you want to compare the time it takes to read from DB2 and load it into the Spark data frame, so this starts at around like 141.10 and it finishes at around 141.15. So yeah, it took around 5 seconds. 4 point whatever, so around 5 seconds. The previous one was around 7 seconds, so kind of close. This is just to give you an idea. I mean, these time intervals are not representatives or do not signify anything per se, but this is just to give you an idea of, okay, what are the different ways in which I can do it, and what would be, I mean, if you just want to get an idea of how the different times may compare, so this can give an idea of, okay, how much time a direct file load versus a read from database might take. Now, there are a lot of factors on which these things depend on. It can depend on, say, for example, the network between your DB2 server and the WSL server, or it can also depend on the way the DB2 is configured, whether it's configured as a columnar database or whether it's configured as an in-memory with enough memory to accommodate these tables, or if it is configured as an MPP, which means it can parallelize a lot of these queries and make them faster. In addition to how big the data volume is, in our particular case that we are using here, the data is just 1 mil, and hence the difference may not be significant. But as you go to bigger volumes of data, like tens of millions of data, hundreds of millions of data, you may start to see significant differences here. It also depends on, apart from the volume of the data itself, it also depends on how that data is distributed. Usually, if the data has a good hash and it's distributed well, and I'm using an MPP kind of database, then the parallelization works a lot better, and then the parallelization can help to read the data a lot faster than the scenario where the data is skewed and the parallelization is not that great. So it can also depend on the infrastructure, like the type of disks we have, the amount of memory we have, the compute we have on the database side. If it's a really small database like the one that we are using here today, one with a 4-core, we may not have enough power or enough capacity available on the database to do all these heavy load activities. So there are a lot of factors on which it would depend on, but typically for your scenario, generally the case is that these databases are big, they are MPP and they are data warehouse kind of implementation, and usually you will find reading from the database may be slightly better than trying to read it from the Watson Studio local storage into the Spark cluster. But nevertheless, I mean, you're free to try it out in your environment and see which one works better for you. So once the data is loaded into the Spark data frame, then the process, it doesn't matter how we load it. So once we have loaded into the Spark data frame, then the rest of the model training process would be the same. And that's what we have done in the next few segments of the code. We are looking at the schema. And then once we know the schema, we are trying to see how many records we have. So this, for example, shows that I have around 1 million records in this. And then we are trying to see that what is the distribution of the records in terms of the label. So here majority of the records are with label 0. This 30% or less than 26% or whatever is with the label of 1. So this is just to make sure that we have enough number of records in both the labels, and this can be used for, the data can be used for model training activity. So once we have validated that, we are splitting up the data into 3 segments, and we are specifying the ratio in which we want to split it up on a random split basis. And the reason we are doing that is to just get some training data and keep aside something for the test data and some for the holdout. Having done that, we can go ahead and create the pipeline. So in this particular case, we are going to use logistic regression for the classification, and this is where we are defining all our features, and then once we have defined the features, we are creating an instance of logistic regression, creating the pipeline and doing a pipeline fit. Now once the model is created, we can run some, using the test data that we had kept aside, we can run the accuracy, and here the accuracy came as 0.98, which is pretty. So Watson Studio provides a set of libraries called DSX_ML, and these libraries provides different kinds of functions to work with the platform, basically work with Watson Studio. So here we are using save function from that set of libraries to save the model that we have just created. Here we have created this model _LR, and we are using that save function of Watson Studio to save this model _LR, and as part of the saving process we are providing having some metadata that can be saved along with the model. The metadata typically we would need to include is what's the name of the model, which one was the test data, what is the algorithm that we used, what's the source that was used to build the model, which is typically this notebook, and then some description around it. And what the system does is, as part of the save step, it not only will take the model and save it as a model in the system, but it will also provide where it has saved the model, and it will also generate an endpoint which can be invoked, which can be called to invoke the model in real time. And finally, of course, we are trying to take a snapshot of the time and see how much time it took to run the whole process. So as you can see, this process took around like 84 seconds. So this is one way in which we can build a model with some sample set of data. This is interactive. The way we have done it is interactive, but then the system also allows us to deploy this notebook as a batch job. And if we want to execute it on batch, which typically would be the case when we are loading huge volumes of data, we may not want to run this in an interactive fashion through the notebook here, as that may require us to wait on a particular step for extended periods of time, and you may not want to do that. So the system does allow you to deploy this notebook as a batch job, and then that can run behind the scene, and then it can take whatever time it takes. I mean, it may not be 84 seconds, it may be a few hours if it's a much bigger data set, but as long as it's a batch job, it can run behind the scene and get the training done on a much bigger training data set. So the end result of all this process of doing the training, building the model, and saving the model would be a model saved under models here. And if you recall, the name of the model that we provide was churn predict. So what would happen is we would have under models, we would have that model created, churn predict. And if I run that script over and over and change parameters along the way, then the different versions of the models will get stored. So here, for example, we can see that there are 4 versions of models. So I have executed that notebook 4 times, and 4 versions of the model has been created. We can go inside the model and see the details around the model, like what kind of schema it has, and other details around what are the features that I've used to build the model, what's the label column and stuff. I can schedule some evaluation on the model, in which case it'll show me the evaluation results here, and I can run some batch jobs against the model, in which case the jobs will appear out here. And all these scripts that I would use to execute the jobs or to run the evaluations will be available under the associated scripts which we are running on the model, using the model. It also the dashboard will also show the accuracy of the model, and for the different versions that I'm building here, it'll show me the comparison between how the accuracy has tracked from version to version. Now in this case, I have actually not changed any parameter of the model, and I've just executed the notebook as is, and that's why you see that there's no change in the queue. But anyways, I mean, the idea is that we can build a model like this, and then once the model is made available, we can run some scoring just to make sure. So this is a web form, sample web form provided by the system, in which I can fill up all the feature values, and I can once I have the feature values available here, then I can test whether the model is working or not, and if the model is deployed properly or built properly, then I will get some kind of result. So once you have tested the model in real time, you may want to actually do the real scoring on a much bigger set of data, and that data could be data which is available as a file, or it could be a data which is available in a database. So the data can be internal or the data can be external, but the idea is that I have a much bigger set of data on which I want to do a scoring. And for that, those kind of scorings, it is not a real-time scoring, but it's a batch scoring. So the system provides you with this capability to do batch scoring. And there are a few parameters you can define for that batch scoring. First is what is the runtime that you're going to use. Now, in this case, we have only one runtime which is configured, which is the local Spark, and in your environment also maybe that's the case. So in that case, we don't have much of an option. But in many environments, we do have Hadoop, which is integrated with WSL, which has a large Spark cluster, or in many customer environments, there could be other external Spark clusters which are much bigger, in which case we can configure such that we have all these Spark clusters which are available here shown in the drop down here, and we can select the Spark cluster in which we want to run it. Now in our case, since we don't have Hadoop configured or integrated with this, it shows me only one option, and that's the one we have to choose. Then next we have to select what the input data is, and then we can that input data could be a local data, so I can choose one of the local files. So here the idea would be that input data I would have loaded up front into Watson Studio, and I could select that, or it could be a remote data, like the data is in a table or a database, and then I'm just pointing it into that table. So the system will read the data from that table and run the scoring on top of that. Similarly, the output data also can be a local file or can be a remote data set. So the remote data set could be a remote database table or whatever, or if it is a local file, then it could be a local file as well. So once you have configured all this, you can take a look at the advanced settings. So this is the script that it will create, and this is the file name, so I can modify it based on what I want to do. So this is, I can call it batch scoring script. And then the job name can be batch score or something, and then we can select the worker. Now for the worker, we were using, it has to be a similar runtime that we used for our training, and for our training we had used this one, Python 2.7, so probably we should select the Python 2.7, and then we had used Spark 2.0, so as part of the environment variables we can specify Spark 2.0, so that this whole runtime is aligned with the one that we had used during the model training. If I need to schedule this, I can schedule this to run on regular intervals, or if I just need to run on demand, then I can run on demand. So we can go ahead and save all this setting, and then we can generate a batch script. So this is the script it would execute in order to do the inferencing based on this input data source, and the result of the inferencing will be stored in this churn predict large out.csv. So we can go through a little bit on the script just to make sure that we understand what it is doing. So essentially, if you see, it's providing which model, the model path from where it needs to pick it up. It's providing the input data as remote input data, and remote input data we would have defined as a remote input data is this data source, and for that data source it is this table, customer churn 1 in table. Similarly, we have defined output data source type and output data source, and all these parameters we have defined here. So output data, for example, is data source output file, which is basically this is the project and then the target, and the target we would have defined above somewhere. Target is this one, churn predict large out.csv, and that's our target. So the script first is setting up these variables and specifying the input and the output files, and then creating a Spark context. And then after the Spark context is created, then it is creating a Spark instance here, Spark context here, and then it is loading the data into the Spark data frame, and then it is going about calling the model and testing the model, right? And then finally, the result, this is the pipeline.load model path, and the result model.transform with the test data set is stored in a data frame, and then this data frame is converted to a pandas data frame, and then this pandas data frame is converted to a CSV file. So when our data volume grows, there may be a few considerations that you may want to take care of in this script. First and foremost, here we can probably modify some of the configurations of the Spark cluster so as to ensure that we have adequate capacity available in the Spark cluster. So for example, maybe here instead of just using the default, which may be just one executor with 2 GB of RAM, we may want to actually specify how many executors we want to use and how many cores we want per executor and how much of memory we want per executor. So that's something we probably want to specify here. So to make sure that the volume of data that we are planning to load into the Spark cluster, at least that amount of memory is available. Otherwise, it'll fail with out of memory error. The second aspect that you may want to consider is where the script automatically converts it into a pandas frame, and this pandas frame is a single node structure which may not have again enough capacity to hold the output data if the output data is significantly big. So we may want to avoid this script, and instead we may want to just directly convert the output Spark data frame. We may want to just use that and create the CSV file based on the Spark data frame itself without converting it into pandas, because if my data volume is huge in this step, there's a possibility that it may fail because this pandas data frame may not have enough memory available to it. So once you have done typically these couple of modifications here, you should be able to run the script and then perform the batch scoring. So just to give you an example of a modified script, let me just quickly show you. So once you have modified those scripts, and if you do the run on, it will save the script under scripts, and then it will submit a job, and it will save the jobs under jobs here on top. But if you want to see how a scoring script will look like, then maybe let's take a look at this one. So this is the same script, but you would observe that there are a few changes that we have done here. So for example, I'm specifying the memory for the Spark cluster. I'm specifying the number of cores for the Spark cluster. If you want, you can specify the number of executors as well. Similarly, down below, what I've done is I've just removed some of the columns that I thought maybe I'll save some space and reduced. So I've removed some columns, but you don't have to. You can use them. You can keep them. And here the change that we have done is I have also commented out this dot to pandas. Instead, I am just taking the Spark data frame and I'm writing it directly as a CSV, and then I've specified the file path in which it needs to save the file. Now, this file path, if you see, this is under datasets. This is a default path in which all the data assets are stored, and that's why I am using it. The relative path is /datasets/ whatever the file name is. But if you want to provide the fully qualified path, then this is the fully qualified path. And how the way you can find this out is by going to the terminal window. There's an access to the terminal window from the project, and in that terminal window you can do a PWD and see the structure of the directories and get the fully qualified path if you need to find out from there. So in the fully qualified path, if you see this 999 is actually the user's ID. So because I have logged in as admin, that's why this is coming as 999. In your case, if you log in as a different user, you will probably see a different number out here, 10 something. But then you can always find this out from the terminal screen that's available, and use the fully qualified name if you need to use that. So once this is executed, there will be a corresponding job. So I can show you some jobs that we ran and the kind of time it took to load this. So for example, when we used the default Spark cluster, this scoring job kind of completed. We can go to the run and we can see how much time it took to complete. So this completed is in around like 3095 seconds, and this is without changing anything on the Spark cluster. So I just used the default Spark cluster of one executor and whatever the X amount of capacity that it had. And then I made those changes that I showed you on the memory and the RAM, and then we reran the same job. And when we reran the same job, I'll show you the result of that job. So that one is this one. It's on the same data set that we are loading, and it took less time. It completed only in 220 seconds. So this is, I mean, we don't have to go with these numbers per se, because this will be relative to so many other factors. But the idea, what I wanted to emphasize on is we have the capacity to modify and tweak the runtime configurations, and then based on that, we may be able to speed up some of our bad jobs as per our expectations. Now, while we do that, we have to also keep in mind that we are not the only user in the system. So if we take up all the resources when we are executing our jobs, others may not be able to log on and do their stuff. So some kind of due diligence will have to be done, or some kind of discipline will have to be maintained in terms of how much resource we want to use, or in the other case, the other scenario that is possible is that as a data scientist, I always run on a smaller set of data, and when I have to run it on a bigger set of data which requires a lot of compute, then we hand it over to the admin to execute it on the WML environment, where things can be executed in a bit more planned way in a type of scheduled manner, such that the different workloads don't overlap onto each other, and they are kind of planned in a manner such that all of them can run on their slot, in their slot, and when they do execute, they get the type of capacity that's required for them to execute. Okay, so with this, let me go back. So what we saw was how to play around with environments, how to configure the Spark cluster dynamically as part of the script, as part of the training script, how to configure the Spark environment for scoring when we are submitting for batch scoring, and we also saw how we can affect or impact the training time and the scoring time based on all these configurations around the environment parameters and all. Next, let us look at how we can do it if we want to push down some of the pre-processing to the database. Now, this might be particularly relevant where I have capacity constraints on the Watson Studio environment. There will always be a physical limitation in terms of the kind of compute that we can scale. And when we hit that, and that is and then the amount of data that we have to process is much bigger than that, then we have to come up with some kind of ingenious ways by which we can still go ahead and do our job without having to break our head over it. So in those types of situations, this comes very handy, like if we can do the pre-processing inside the database itself and then get the result out, and typically we can make the data volume significantly smaller by doing all the pre-processing outside. Continue without kernel. Okay, maybe I'll not execute this, I'll just show you. So here, for example, we are doing the same thing. We are configuring the Spark environment first and making sure we have the right kind of capacity that we need. And once we have done this, we are going to read the data from the database table. But instead of reading the whole data, we want to do the pre-processing inside the database. So here, for example, we had all these features of gender, investment, income, activity, yearly income, yearly transaction, and a lot of these were nominal values. So instead of using those numeric values for the modeling itself, typically a standard practice is always to do the binning and group them into different groups and observe the behavior based on the groups, which is likely to be the case. So what we can do is, instead of doing a select star from the table and bringing in all the data which we were doing previously, here we can do the binning inside the database itself. So what we have done is we have grouped age into 5 buckets, and similarly we have grouped investment into 5 buckets, and all these nominal values that we have, whether it is income or whether it is average daily transaction or whether it is number of tweets, all these features that we had, numeric features, what we did, we grouped them into 5 bins, and then we took the unique set of that based on the level, and all this can be done within the database itself through the query that we are going to submit to the database. And once we do that, the end result, the number of records that we get would be significantly smaller. So here, for example, we are submitting this modified query instead of the select star query, and then we are getting the result out. So if you see, the query execution takes a bit longer, 1 minute 37 seconds, because it's doing a lot of pre-processing inside the database. But then when you see the number of records, it has significantly shrunk from the original number of 1 million plus records to only 4,000 records or 5,000 records, whatever the case may be. Now, we don't have to go by these numbers because that will depend on the distribution of the data values and all. But the idea is that once we have done that, we can manage with a much smaller compute. We don't need a very huge compute to process this 4,000, 5,000 rows of data, right? So maybe now I don't even need a Spark environment clustered across multiple nodes. Maybe I can just run it using the local Python environment that I have. So this is one mechanism by which we should try to do pre-processing push down to data sources. and thereby significantly make it much more smarter way of doing things instead of just using brute force, which we were doing before, right? The rest of the process is same, so the rest of the code is the same, nothing changes. We are still going to apply logistic regression, we are still going to do the fit, and we are still going to save the model in this environment. So that is the third, our scenario 3. So we were supposed to look at 3 scenarios, so we looked at all 3 of them and how they work. Now these assets, I will make it available. I'll make it available so that you can download these samples, and if you need to refer to it, you can refer to it through the links. Now the other aspect of it is, once you have defined all these models, they can come in versions, and then you can compare the versions of the different models. So, for example, this one has 4 versions, and this one has 2 versions. This one, for example, also it was built twice, and there are 2 versions. So, system automatically keeps track of these versions. And if you want to compare these versions, then there's this concept of model groups. So you can create a model group, and in this model group, you can assign one model as the champion model, and the others as the challenger models. So here, for example, we have 2 models, version 1 and version 2. And then if you want to look at the evaluations, we can get a comparison of the evaluations. You can choose what kind of accuracy metric you want to use. Now, in this particular case, the models were like the same models, so all of them look similar. But we can see, based on if you have multiple evaluations, it will show here, so we can compare the different evaluations run between all the different models and see how how the accuracy compares between them. So with that, we come to the end of today's session. So in this session, the idea was to see what are the options we have, and what are the considerations we have if we want to run big workloads in a Watson Studio sandbox environment with limited capacity. I hope that you found it useful, and you will be able to leverage your own environment, Watson Studio environment, based on what you saw just now. So thanks for listening. Have a good day. Bye-bye.